So hi everyone, hope you're all awake here after lunch. I come from Arcam. I think we've heard already I've heard people mentioning EBM already. I'll take it up a little bit for those of you who are not familiar. I'm going to do a very brief recap. Let me see if I get this. Oh yeah. So I'll start with presenting Arcam, who we are, what role we play in this industry. Then going into some about EBM, describing what we are and what we do. And then just digging a bit deeper, getting very technical. I'm going to talk about some of the development we've done on our cobalt chrome process, giving some examples of how we work when we develop our processes. Some of the application, material properties, and osseointegration, which is boning growth of cobalt chrome. And a lot of this is work we've done in collaboration with Chalmers and GU, so there's some people in the room that's been involved in this work as well. So to start off, Arcam, who are we? I mean, we started as a very small company here in Gothenburg, but today we're a very big group in the world. So we have our section that's called Arcam EBM, which make additive manufacturing systems, services. We also realized, and I think we learned more from MTC earlier today about powder and what important role they play in our materials, and we realized that also. So we actually went to buy a company in Canada that manufacture powder, so they make high quality titanium powder mainly. Also, we have a company that's a contract manufacturing in the US for medical implants that's called DTI. And together all these sections of the company really gives us a broad knowledge about additive manufacturing, how we're using it, and how we're producing parts with it. As I said, we started as a small company in Mölndal here in Gothenburg. Today we're a worldwide company, so we have our headquarters partially here in Sweden, but also outside Boston in the US. Further, we have some local companies, China, Italy, Germany. Actually, this one should be marked as well. We have one in Germany, UK, US, and we have a lot of sales distributors around the world as well. So the EBM technology, I'm going to give a short recap. Who in here are familiar with the EBM technology? A bit more than half, okay. So it's a powder bed fusion technique. It's a vacuum system, and what differs us from a lot of other players in the powder bed fusion market is we work with the electron beam. That's our energy source. That's what we use for heating, melting, and everything we want to do. So just because we have an electron beam, we can use a very high power and we can be very effective and fast in what we do. We can also use magnetic coils for moving the beam, so we can easily adopt the focus and the placement of the beam very fast, which allows us to have high productivity, but we can also speed up the process. I guess with the focus as well, one thing we can do, we can actually heat every layer. I had a discussion over lunch about the heating, but this allows us to actually going down here with a hot process, we don't get residual stress in the material. So the material coming out of the machine, depending on the material, might not need any heat treatment. But I'll talk more about that in a bit. And it's also a vacuum process. First of all, it's needed just because we have electrons. If we're going to control the electrons, we need a vacuum process, right? But it also gives us a very nice environment for building parts, so we can really control it when we work with reactive materials. And titanium is one of our major materials, and it's very good to work with in vacuum. So the buzzword today, if you haven't realized, it's solutions. We've heard that in several presentations today. We work with metal additive manufacturing, and we're trying to look at the whole perspective. And we focus on two main industries, which is the aerospace, which you just heard about, but also the orthopedic industry. And I'm going to talk a lot about the orthopedic industry today as we dig deeper and get a bit more technical. So for the orthopedic industry, there's a lot of implants actually out, and they've been out on the market for a very long time. We started in 1997, and 10 years later, there was a CE-certified product out in the market that started to get implanted. And that's from Lima Corporate. They're based in Italy and do a lot of hip cups. And you can see they were the first ones, but today there's over 100,000 cups implanted. So additive manufacturing is really starting to become mainstream. It's not a very new thing. It's well accepted in the orthopedic industry today. So there are several FDA clearance and the Chinese version of FDA as well, where there's a lot of different products out. So going into some more materials and applications of additive manufacturing techniques, I'm going to talk a little bit about cobalt chrome today and its application in the orthopedic fields. And it's been used for a long time. It's been used since the 1960s for implants. And the main applications are different bearings, basically, in the body. It's a very wear-resistant material, and it's corrosion resistance, which means we have it on hips, knees, different kinds of joint replacements, but it's also commonly used in dental applications. And just because of the wear properties, it's very nice to polish for the bearing surfaces. So I'll talk about 3 topics on cobalt chrome today: the application, material properties, and a little bit also about osseointegration. So to start with the application, I mean, it was brought up earlier today as well. Complexity is really free when you work with additive manufacturing, and one of the main benefits, especially when you talk about the orthopedic industry, is you can make this kind of structures that allows boning growth. And it's commonly seen for titanium implants, but it's also feasible to do with cobalt chrome. You can do different kinds of random regular structures. You can do small parts, you can do big parts, you can make different series just by using the full build volume that you have. For a small company or a big company, this technique is actually suitable. You can make different sizes in the same build, or you can make one size if you want to work it in serial production. Or if you want to make more customized parts, you can also stack them together in one build. Going a bit more into material properties, I'm going to exemplify this a bit more and talk about our development, some of the development of our materials. But typically what we look at is the strength of the material and ductility. It's one of the first thing we evaluate when we work with a new material. And for cobalt chrome, we're looking at the F75 standard. So I'll go through a little bit of data. Everyone loves data. I love data. Looking at yield strength, we have one group first, which is as built. I won't go into the different groups, so this is different parameters we've tested. So this is as built. You see a red line. This is the acceptance limit from the material standards, and you can also see the post-hip data. What we see here are some different trends, and I'm also going to pull up the ultimate tensile strength. So before we actually hip cobalt chrome, we can see most of it actually applies to standards, not here. When we hip it, we lower the yield strength a little bit. We see a little bit of a change in the ultimate tensile strength, but the main difference we see is we actually remove some of the anisotropy we see between the gray, which is Z, and the X and Y, which is blue. And I'm going to go in and talk a little bit about this later on, but this is related to the microstructure and the changes we make when we hip this part. So if we're looking more on the ductility properties, elongation and area reduction, we can see that actually before the hip process, in the as-built materials, we don't really apply to the material standards, so it does need a hip process, and then we're well above the standards. Again, we can see that the behavior between the Z direction, which is actually horizontal bars, and the X and Y, which is vertical bars, and the horizontal bars is actually reduced after the hip process. So if we dig a little bit deeper to understand this, If we look at the microstructure of the as-built material, it's a columnar, a very directional microstructure, and has a very fine grains. So this is the behavior we see, we see a different behavior in the Z direction and in the X and Y. But it also has very brittle properties, as you can see on the elongation and area reduction. We could also see some traces of porosity, and this originates from the manufacturing of the powder. Then when we have, after the HIP process, we can actually see that our microstructure is equiax, so it's the same in both directions. We can see an effective removal of the porosity, and we can also obtain the kind of microstructure that we want for carbides. They actually dissolute, which is an important parameter when you talk about cobalt chrome. Digging a bit deeper in the structure of the material, we can look at the face of the material as well and how that changed when we actually do the HIP process. So you can see, depending on, so you have the temperature, chrome content. So when you manufacture something at the high temperature, you can get the gamma structure. At lower temperature and quick cool down, you get the epsilon structure. And what we're looking for here is actually the gamma structure, because does not have a brittle behavior that we see for the epsilon structure. If we then look at what kind of structure we get on this material with the XPS analysis, we can see that on the as-built, we actually obtain a very high. So yeah, we tested some different carbon content powder. So we can see that it's a very high percentage that's actually epsilon, which we don't want to see. Whereas when it's hipped, we don't get that. Instead, we do get the gamma structure, which is what we wanted to obtain. So that was a little bit about the microstructure, some of the things we dig down into when we develop different types of materials. If we also look a little bit at osseointegration, this is a very good publication. I think I did see Anders in the room. He's in the back, so if you have any detailed questions about this study, he's happy to answer that. I find this a very interesting study because it compared titanium 6-4, which is a well-known material for osseointegration, and we know the body really likes titanium. But what happens when we start building the same kind of structures with cobalt chrome? Can you still obtain the same bone ingrowth? So first of all, this kind of structures were manufactured, they were implanted. But when you really look into what the surfaces look like on different length scale, in the top here, this is more on the millimeter or hundreds of micron scale, here's micron scale, and then you have the nanometer scale. What I find really interesting, especially in the medical industry, when you look at additive manufacturing, is you do obtain this kind of roughness on all different types of levels. So you can get good attachment from cells, etc. So both you can get bone ingrowth on this level, but there's nice possibilities to do attachment also on a higher scale. Without going into too much detail, the conclusion of this study was actually what they could find was you get a similar behavior of the bone ingrowth between cobalt chrome and titanium, which really means that in the same way you've been working on titanium for bone ingrowth, you can actually use cobalt chrome parts to do so as well. So talking a bit more on the EBM process and how we work with cobalt chrome and how you can build parts with the EBM process. So for cobalt chrome, we have a build envelope of 200 by 200 by 180 millimeters, which is this volume you see here. What I think is very interesting, especially talking about machine time and productivity in additive manufacturing, what we're allowed to do in our process, partially due to we're having a hot process, we can actually stack parts, so you can really get good productivity when you want to manufacture a serial production. So in this build, for example, it was 38 parts, but if you actually count it down and want to say how long time did it take per part to build, it's less than 2 hours. So another thing we can do is we can simply remove things from the start plate. There's no need for wire cutting. We've had this for our titanium process before, but we also have it for our cobalt chrome process. I think you all saw from the presentation here, I'm going through the details about the HIP process. It's something we need for our cobalt chrome in order to obtain the right microstructure, but also the material properties that we need. But what a lot of this development work that I showed you has led to is actually we don't need, previously we needed a heat treatment to actually obtain the right microstructure, which we now are able to remove in this new process. So there's no need for stress relief, which we've never needed, but we don't need any heat treatment or homogenization either, which is a good benefit and really removes some of those post-processing steps that takes time. So, in summary, the application of cobalt chrome in the orthopedic field is pretty big. It's hip, knee, joints, dental, but also we've been discussing that a lot today. I mean, a lot of our young engineers and design engineers need to start learning more about additive, and I think there's a lot of more applications that sometimes we have a hard time seeing. Just because we don't think additive enough. So I think there's a lot of more applications out there that we need to look at as well. Some more material properties that I presented. So our processes apply to the F75 standard, and it's needs of a HIT process, but no other or further heat treatment. And also for osseointegration, it can actually show to have a similar behavior as titanium in the study we showed. I'd also like to acknowledge there's a lot of collaboration partners and data that I presented today that comes from a lot from these universities here. And I did bring a little bit of a bag with some implants here. If anyone's interested, feel free to come up afterwards and have a look at them. Some cobalt chrome parts, tibial trays, and spinal knees as well.